In this lecture, we are going to start with the second part of the unit 2, which is a rotational motion. Now, motion of the particle from one position to another position could be in a straight line or it could be in a curved path. I'll draw it here only. Suppose this is position 1 to 2. So the motion of the particle from one position to the another position, it could be the straight line or it could be the curved path. So it could be a rectilinear motion, or the motion could be a curved path or the trajectory. So whenever the body moves along some curved path, so that body is moving along some axis of the rotation. So in this case, we call as the motion of the body as a rotational motion. Suppose this is a block, metallic block, and this is moving along its own axis. This also comes under the rotational motion. Or if this block is moving along the curved path like this, so this also comes under the rotational motion. So when the body is moving from one position to the another position in a rectilinear motion, we call the displacement as r, and here the displacement is in a angle, so it is measured in a theta. As the body is rotating, so this block, when it is rotating or when it is going from this position to this position along some curved path, so the displacement will be along the axis of rotation and it is measured in this theta. So in a rectilinear motion, the displacement is a straight line. It is measured in a distance. It is measured in centimeter, kilometers, meters. So let omega be the angular velocity and let v be the linear velocity. Then there is a relation between these two also. This v is equal to r omega. This we have seen in the 12th standard also. So the velocity in a rectilinear motion is given by v is equal to dr upon dt, whereas the angular velocity is given by d theta upon dt. Obviously, velocity is a rate of change of displacement with respect to time. In case of the trajectory motion or the rotational motion, the displacement is theta. Therefore, angular velocity is given by rate of change of displacement with respect to time. Similarly, momentum in a linear motion is given by P is equal to mv. In a rotational motion, angular momentum is denoted by L and it is given by R cross P. We can put the value of this linear momentum. This is nothing but the linear momentum. So this is nothing but mv, and we can also put the value of V as R omega. Therefore, it can be written as m into R into omega. In a linear motion, according to the Newton's second law, we say that F is equal to dp upon dt, rate of change of momentum with respect to time. Similarly, the force required for the rotational motion is called as a torque and it is given by dl upon dt. Kinetic energy in case of a linear momentum is given by 1/2 mv square, whereas the kinetic energy in a rotational motion is given by 1/2 m r square omega square. V is equal to r omega. Therefore, we are just putting the value of r square omega square as a v square. Now the rigid body is one whose shape remains constant under any kind of a motion, whether it is a linear motion or it is a rotational motion. So this is a particle in which there are number of particles. So when this body is moving along the curved path, so each and every particle is moving along the curved path. So when this body tries to move from this position to this position or along its own axis, then each and every particle will follow some same rectilinear path. So the angular displacement will be same for the all particles. Now The moment of inertia is one more important term which is related to the moment of rotational motion. Momentum of inertia is defined as I is equal to summation of MI/RI square. So where I runs from 1 to n. Suppose this is a body with having n number of particles, and each number is, so each particle is having mass ranging from m1 to m2 up to mn. Now consider this body, it is rotating about its own axis. Let's call it as O dash. Then moment of inertia of this body is defined as summation of a product of all the particles and a square of its distance from the axis of the rotation. So we know that this summation of mi, where I runs from 1 to n, will be capital M. So I is given by m into capital R square. Thus the moment of inertia is defined as the sum of products of mass of each particle in the body with a square of its distance from the axis of the rotation. Actually, it represents the inertia in a rotational motion. We know that the inertia in a linear motion is defined as a tendency of the body to resist the rest position, or to resist the linear motion. Similarly, moment of inertia is a tendency of the body to resist the rotational motion, which is called as a moment of inertia. Now once you know this moment of inertia, we can write the terms angular momentum, kinetic energy in terms of this moment of inertia. Now this m r square omega square can be written as L is equal to summation of this m I r I square omega, where I is running from 1 to n. We know that the style of the physics, this mi is nothing but any particle which is chosen randomly for the experiment or to calculate the angular momentum right now. So this mi is the mass of the particle, ith particle, ri is a distance of that particle from the axis of the rotation, and omega, it is constant for all the particles. So we have not taken omega I here because this omega is constant for every particle, whereas this mass is changing for each particle. The distance from the axis of the rotation is also changing for the every particle. Therefore we have written mi ri square omega. So it will be equal to, we know that the summation of mi ri square is nothing but I. Therefore L is equal to I omega. Kinetic energy, the total kinetic energy will be given by summation I runs from 1 to n 1 half mi ri square omega square, which is equal to I omega square. So this is nothing but the kinetic energy in a case of the rotational motion in a form of a moment of inertia. So this is also kinetic energy in form of a angular velocity, and now this is the kinetic energy in a form of a moment of inertia. So this moment of inertia can be written in a form of a radius of gyration as m into k square. Suppose let us consider this plane. So this plane, in this plane there is a point at which if I hold on the so this plane will remain steady. So that point where whole mass of the body is supposed to be concentrated, it is called as the, so this is called as the center of the mass. Okay, and the distance from the axis of the rotation, if I am rotating the pen in this direction like this, so the axis of the rotation will be here. So this will be the axis of the rotation, but the whole mass of the body is supposed to be concentrated at this point. Okay, so distance between the axis of the rotation and the point where whole mass of the body is supposed to be concentrated, it is called as a radius of the gyration. Now let me draw it here. Suppose this is a rod, and for this rod the center of mass is nearly here. So this is the point where whole mass of the body is supposed to be concentrated. But if I am rotating this rod from the one end, okay, so distance from the point where whole mass of the body is supposed to be concentrated and the axis of the rotation, it is called as the radius of the gyration. And mathematically it is represented as, so this we know the equation I is equal to summation of mi ri square. I runs from 1 to n, which is nothing but I runs from 1 to n m1 r1 square plus m2 r2 square plus up to mn rn square. So if the mass of each and every particle is the same, we can write the same equation as m into summation of I runs from 1 to n r1 square plus r2 square plus r3 square plus up to rn square upon this n. Or we can also say that it is nothing but the I is equal to m into k square, where k square is equal to r1 square plus r2 square plus up to rn square upon n, or k is also called as a square root of r1 square plus r2 square rn square upon n. So mathematically, root mean square of the position of the rigid body. It is nothing but the radius of the gyration. So the physical significance of the radius of the gyration is that if you want to rotate any body, suppose this is a door, and if you want to rotate about this axis, so this door is fixed here on the, so this is the axis of the rotation, and if you want to rotate the door, so you must know that if you are moving away from the radius of the gyration, so if you are applying some force over here, so it will be easier for you to rotate the door. Okay, as you are moving close to the axis of the rotation, you have to apply more amount of force. So the physical significance of this radius of gyration or the moment of inertia is that if you want to rotate some heavier bodies, then you need to know the laws of the rotational motion. So this moment of inertia has a formula I is equal to mr square, and from this formula we can see that this moment of inertia is dependent on mass of the body and its distribution of the particles about the axis of the rotation. It will also depend on the shape of a body and position of the axis of the rotation. First, suppose if this is a rod, so its moment of inertia passing exactly through the center, passing from one end and passing from the middle of the one end. So moment of inertia for each and every axis of the rotation will be different. Right? So in the next lecture we are going to see the different moment of inertia about the different axis of rotation for the different shapes.